what do these things look like, and therefore, what kinds of ways do we have to describe how this moves? Okay. Well, let's start with displacement. And here's my displacement graph up the top. It looks just like a regular log curve, except it's been shifted 1 unit to the left, right? Okay, now, therefore your t equals 0 asymptote is really a t equals -1 asymptote. And then when you draw it, it should pass through, oh, I missed. Oh well, sorry, use your imagination. You should pass through the origin, right? Now, that's terrible. That's irredeemable. Oh well. Now, here's a question for you. I gave you very, very little information when I described the situation. I just gave you the equation and I told you a starting point, didn't I? What would you conclude, therefore, about what kind of restriction we should make on this? I mean, there's already a restriction, namely t is greater than -1, non-inclusive, okay? What else would you say? Are there any other restrictions, or is that the graph? Now, see, I would be inclined, with no other information, right? I would be inclined to say, actually, there's a restriction, time is greater than or equal to 0. That tends to be the assumption if you don't know anything else, okay? Particularly when they say it starts somewhere, right? It's like, well, if this is where it starts, where was it before? There was no before. If I have some part of the graph over here, for instance, right? Like this point here, I would say, well, that's where it starts. Like, that's the real start, right? So your kind of default is for time is greater than or equal to 0, unless the question sort of provides to you some situation where, you know, at 3 o'clock I was here. So obviously there's a meaning to negative time. You know, it's before 3 o'clock, okay? But here with no other kind of conclusion, that's what I've got. All right, great. Now, there's my displacement function. What does my velocity look like? Well, like before, it looks just like a regular hyperbola, except it's been shifted 1 unit to the left. Okay. Now again, when you think about this, right, it probably will help to actually have some decent scale on here. This part of the graph, right, I mean, a normal hyperbola looks like that, doesn't it? Okay. So this is being moved 1 unit to the left, so I'm getting this kind of shape. Okay. But in order to reflect the fact that, I mean, up here my displacement doesn't exist anywhere except for t is greater than or equal to 0, I'm going to apply the same kind of restriction to this graph. Okay. So it looks like something like this. Is that okay? Does that gel? And of course we have that intercept there, that should be 1, right? T equals 0, you get 1 over 1, no problem, okay? And you can already, hopefully, start to get the gears turning in here for what this implies about this, what it tells you, what information it provides you about the motion. All right, one last step. This is the graph we've got to come to terms with. How is it different to this graph? It's upside down because of this negative, right? But that's not the only difference. There's another difference, right? What does that mean? If I think about it this way, right? Let me think about it as t approaches infinity, okay? Both of these are tending towards 0, right? But this one is tending faster, right? Because the denominator is growing faster. So therefore the denominator is growing faster, so the whole number is approaching 0 faster. It's pretty hard to actually reflect that on the graph because the shape of it is so simplistic, but it's important to keep in your head anyway. So, I would still have the same vertical asymptote if I went there. I'll have the same horizontal asymptote. What's my x-intercept? It's -1, isn't it? Okay, and you can get that just by putting time equals 0. Great. That's all the information we need. I should probably label this too. Now, the question is, what's required when you have to describe the motion? You've got to put this into words, okay? It's unfortunate that we had to do this after the English assessment, isn't it? But there are 3 very simple ingredients for describing motion, okay? And I used to see, you know, students would sometimes, they would take, like, actually, really is unfortunate this after English, they would take a page, and sometimes the motion of a particle like this, they'd take half a page to describe it, okay? And in some ways, There are a lot of things to say, if you wanted to say lots and lots and lots, right? But we don't. We just want to wrap our head around, like, basically, like, actually, as an HSC keyword, I think describe means, like, identify key features. That's the general idea, isn't it? So you're not telling me about every single detail, like, what, you know, I got up and I had breakfast. And no, you're just giving me the big things, and that's these three things are. Okay. So, no prizes for guessing what the first thing is.
Ice cream.
I'm going to stop doing closed passages with year 12, don't I? A is for apple. I is for ice cream. IC. IC is not for ice cream. IC is for initial conditions, okay? Initial conditions. You guys are worse than me. Okay, anyway. Now, initial conditions, what does that include? Well, you need to know... You need to know where you are. And you need to know where you're going. That's all. Okay. So, what that means is, you need an x value. Okay. X value. Now, this is a bit tricky, I admit. I'm not sure how else to describe this in a non-arbitrary way. This is an x, this is a displacement. Obviously, this is referring to where you're going. That's a velocity, isn't it? Right? That tells you where you're going, right? Well, I should say where you're going, right? Now, here's the thing. They almost never care about, unless they specify, they don't care about the velocity's value, right? They don't want you to say 1 meters per second, right? The reason why is because if I went and asked for every single value, this would take half a page, okay? All we want to know is that you can describe features off of what a graph looks like, okay? So more often what they really want is just the sign, okay? Now, what that translates to is you would say the particle starts at the origin and is moving in the positive direction. That's what you'd say. Or it's moving up, or it's moving right, whatever the question provides to you. Okay? So, you want an x value, the actual position where you are does matter, and then you want to know, are you going up, are you going down, are you not going anywhere? Like that would count as well. If this was a stationary point, you would say the object begins at rest, is the way the questions tend to supply it. So, sign would be positive or negative or 0. That is relevant. Okay? Right, now, when we're talking about major features, what might be the next important thing that happens? Well, you want to know if this thing is moving around and if this changes, right? If you go somewhere else and then this, you know, your movement in a particular direction, if it turns around or if it stops. So geometrically speaking, what are those places? Stationary points. Well done. Are there any stationary points on this?
No.
There aren't. It's worth mentioning, by the way, I'm talking about this guy up here. When I say stationary points, I mean stationary points for displacement, not stationary points down here or down here. If you were describing every single feature of velocity and acceleration, again, you're going to get half a page or more, actually. You need to know stationary points. You need to know not only where, but this time, you need to know when. Right? So you want to tell me, for instance, not in this case, you know, I stopped, 2 meters to the right of the origin after 3 seconds. Right? So you want an x value and t value. Okay? Stationary points includes when it doesn't turn around, when it just stops. Okay? And then continues, which I guess would be a horizontal point of inflection. Okay? So this includes all of those. If you turn around, then you should say your new direction. If you don't turn around, you say then continues in the, and whichever direction you're going. Okay? But in a similar way to up here, right? You're providing a sort of marker. Here's where I am. The reason why you don't need to provide a time here is because it's the initial condition. But here, it's like, well, where are you? When are you? And what happens then? You stop, turn around. Stop, keep going in the same direction. Okay, now, last one. I won't make you guess this one. You need to tell the actual question, where are you ending up? What is the final state of the particle? Object, whatever it is that's moving. Okay? Now this is tricky. This is not like these. These are actual points usually, okay, and something happens at those points. Now this is kind of a bit of a wild west of anything can happen. Let's have a look at this, right? How would you describe what this thing is doing as time approaches infinity? That's what this is. If there's no endpoint. How would you describe it? Well, that's where you start to appeal to your other graphs. Okay, well, I mean, you do appeal to your other graphs all the way through, but here's where it's most important. Okay, does it ever turn around again? No, it doesn't. Otherwise, you would have described it up here. Okay, you never have turns down here because it's the final state, right? So therefore, it's always going to be moving after any stationary points I have to describe. It's always going to be moving in the positive direction, and I can read that off this. See how the sign of velocity is always positive. So I'm always going to be moving in that direction. Okay. So that's talking about velocity, but I'm trying to describe the final state as t approaches infinity. So not only do I want what the velocity is, I want to know what it's going toward. And you can see what it's going toward, can't you? Right? So rather than saying the velocity of the particle tends towards 0, how would you word that in a describing motion sort of phrase? You'd say the particle's slowing down, and it is slowing down forever, right? Does it ever stop? No, it never stops because it never gets to, the velocity never gets to 0, okay? So you can see what I mean by how do you describe this final state. It's difficult for me to give you a checklist because, for instance, some particles do have an endpoint and they stop and that's what they do, okay? If you're doing simple harmonic motion, obviously you don't have a kind of, it just keeps on doing its thing, right? But you need to talk about where it ends. So let's do that now. Initial conditions, I've already sort of worded this, but let's write it down together. Okay. Initially, we begin at the origin, okay, and we are moving in the positive direction. I'm going to abbreviate a little bit just because it takes me so long to write things on the board, but please do write the full words, okay? So that's that. You may even like to put down, like, just like in mathematical induction, just headings for yourself. Like, okay, this is my first thing. Now I move on to the next thing. Now, it just so happens that in this case, there is no next thing. It never turns around, okay? When I describe the final state, okay, that final state actually describes everything in between from initial condition to. So this is part of why I chose this. It's a very boring example. It's simple to describe. Okay? So there's nothing under heading 2 for this. But under heading 3, right, I would say the particle continues because it hasn't done any turn or anything like that. It continues to move in that direction. And I can say slowing down forever but never stopping. Okay. If I did have some stationary points, I might have to invoke this acceleration language in here. I might have to say, for example, it slows down and reaches such and such a point, and then it keeps going. Or it slows down and reaches such and such a point, and then it turns around. All of that language will be included in here, but thankfully we've got a nice simple example. That's it. Okay, so there's nothing too mystifying about describing motion. People get intimidated because they're like, oh, words, commas, full stops, but all you're trying to do is interpret. That's all you're really doing. Okay, and you can be as minimalist as you want, so long as you adequately describe the motion.